Welcome class to lecture 2.2, the time value of money. This lecture will follow roughly with chapter 5 in your textbook. As you can see, I've also listed some practice problems for this class. There's some questions listed for each different type of question type. Now these practice problems are just practice. That means you will not be graded. And if you'd like to challenge yourself or get a better understanding of the material, you are more than welcome to complete all of the problems at the back of each chapter within the textbook. Now the time value of money is one of, if not the most important concepts in finance. And time value money is simply the concept that a dollar today is worth more than a dollar tomorrow. I can prove this really simple by giving you the choice. Assume that I gave you the opportunity to pick between $1 million check right now that you could go to your bank and cash, or the opportunity to get $1 million in 10 years. Which choice would you take? Choice A, the $1 million now, or choice B, the $1 million in 10 years? Everybody would, it's rational, would assume that they would take that $1 million now, right? You could invest it, it could become worth more. You get the money, so you have certainty. You don't know what might happen to me within 10 years. Let's face it, I could get hit by a bus, on my way home today, and it'd be real hard then to collect on a promise I made during a lecture, right? But if you got that check in hand, took it to the bank, and they put the money in your account, you sure would feel a whole lot better about getting that $1 million. A more interesting question might actually be, what would you be willing to take in 10 years to wait 10 years instead of taking the $1 million today? Would I have to give you $2 million in 10 years? $3 million in 10 years? $4 million in 10 years? $5 million in 10 years? $10 million in 10 years? $100 million in 10 years? There's a lot at work here. For some people, that $1 million today would just change their entire world. So it'd be very hard for me to put a price on 10 years from now, and especially if maybe somebody doesn't expect to live for 10 more years. On the other hand, somebody might mathematically calculate what a good return would be and what that would be in 10 years, and see if it would be a better investment for them to wait the 10 years to get the money. Now, how would you go about doing that? Well, today we're going to actually look into that. Okay, Ross, I'd now like to switch to the next slide. Now, in order to be able to mathematically that question out, we have to first develop some key concepts and skills. There are 4 different buttons on your calculator in the time value money row, which I'll show you in just a second. They are the future value, present value, the I button and the N button, or the interest and the periods per problem. So each of those buttons actually represents something very specific. The first button is actually going to be the number of periods, and that's just how long you are investing. The next button will be the interest button, and that button has with the interest rate or discount rate for a problem. The next button is the present value, so the present value of the cash to be received at some future date. So that's where you might discount back future cash flows to figure out what an investment's actually worth. And then the future value of an investment made today. So if you put your money, like if you got the $1 million check and you invest it, what could it be down the road? Now, I would like for you to be able to solve these time value money problems using the formulas and also an Excel spreadsheet. But the real key skill that you'll have to do is to learn to solve these problems using your financial calculator. Okay, Ross, I'm going to switch to the calculator slide. Now, the calculator I would like for you to use in this class is the Texas Instruments BA2 Plus. And as you can see, in the long rectangle there, I have drawn attention to the time value money row. These are the buttons that I was talking about previously. So let's go over them one more time since they are so important for today's lecture and for this class. The first button, which I call the N button, is going to be the number of periods, and sometimes you may also see it as a little t in equations. The next button says I divided by y. However, I don't like the divided by y. I wish it just said I, because we're not always using years. That stands for interest per year. I look at it more as a periodic interest rate or an interest rate per period. And sometimes you will see this as little r in equations. The next button is your PV or present value button. The next button is the payment button. And for now, we're going to assume that that is going to be 0. So for all the problems we do today, you don't really have to worry about the payment button. Just make sure you put 0 in for it. And the future value is the last button. Now, one thing that you really want to pay attention to, and I made a note here, is that either the future value or the present value must be negative. So even though in the problems they're going to give you a positive amount for these amounts, for the calculator it has to assume that somebody is putting money into this system at some point. So either you're putting money up front, so your present value would be negative to get a big positive return down the road, or you're the opposite, which is perhaps like a bank where you are getting a loan from the bank, so you would get a big amount up front and you'd have to pay that off back over time or with one big lump sum down the road. So then in that case, the future value would be negative. Either way, even if you didn't understand what I just said, just remember that you're going to get an error if you don't have at least either the future value or the present value as a negative number. All right, now I would like to switch to the basic definition slide. So let's talk about a few basic definitions real quick. First being the present value. The present value is the current value of future cash flows discounted at the appropriate discount rate. In other words, what would I pay today for the cash flows that I expect in the future? For example, look at stock prices. Stock prices are the present value that you would pay for a share in a company today based on what you expect to get back from that company down the road, whether it's an increase in the stock price, which is called capital appreciation, or whether it is payments made to that shareholder in the form of dividends. But you would figure out what those values are and discount those back to today and figure out the stock price. And that's essentially what you do with most investments and a lot of other issues that arise with the time value of money. Future value is the amount of an investment after one or more periods. So we're talking further down the timeline. So when you use a timeline, or if you look at some equations, how they're written, little t will be 0 for present value, and it will obviously be some number higher for future value because it will happen at a later period. Okay, Ross, I'd like to move on to the next basic definition, interest rate. Now, if we take a look at the interest rate, this is one of those situations in finance where there's a lot of terminology means the same thing, very much like earnings and net income. But with interest rates, there's a whole lot of different things that may be referred to as. Interest rates can sometimes be known as little r or big I. They're sometimes called the discount rate or the cost of capital or the weighted average cost of capital, which is the WACC, opportunity cost of capital, the required return. It all depends on the usage. For example, a lot of times you think of the interest rate as what you might get on an investment going forward, whereas the discount rate would be what you would discount future cash flows to, what you would use to discount future cash flows back to the present. So those are maybe arrows pointing in, opposite directions on a timeline, but the actual percentage is the exact same. As for the weighted average cost of capital, we'll talk about that at the very end of this class. It's pretty much the last module or the last exam in this class. And required return, we'll talk about it in several different ways in this class, especially when we get into internal rate of return and net present value, which are on exams later in the class as well. Okay, Ross, I'm going to move to timeline of cash flows. Now, to think about the N or number of periods, let's first define tick marks. They're basically just the lines at the ends of periods. So the present value times 0 is today, and then time 1 is the end of period 1. Now, some of you won't need to draw cash flows to figure out problems. Others will find it very helpful. It's really up to you. However, I wanted you to expose you to one right off the bat so that you can start to see how you might go about creating a timeline. Okay, Ross, I'm going to go to the next timeline slide. For example, let's look at a very simple timeline for a $100 lump sum that's due in 2 years. As you can see, in year 0, there's not anything written there. And you go 1 year, you go 2 years, and there's $100 written there. Now, this is a very simple problem that you could use to first learn how to use your calculator or to use the equations. Let's take a look at how we would do it either way. Okay, Ross, I'm going to go to the next slide. Let's take a look at the equations first, the general formula for calculating future value. This is one of the most important formulas in finance because it pretty much captures the time value of money. Now we will go through each of these variables, these 4 variables that we have talked about repeatedly already within this lecture, and how you would solve it. Now, solving for future value using this equation is not that much more difficult than using the buttons on your calculator. Solving for present value is also not that much more difficult using the formula than using your buttons on your calculator. However, once you get into solving for the interest rate or for the number of periods, a lot of you will start to realize that it is much easier to use the buttons on the time value money row on your BA2 Plus calculator than using the equations. In other words, all the formulas are just a variation of the formula above. However, it can get extremely difficult when you start solving for a value that's an exponent like t in this formula. Okay, Ross, I'd like to move on to the next slide. Now, looking at the future values, so let's just, use the basic formula. Let's try to solve the problem we had before where we had $100 coming back in 2 years. Let's make it even easier. Let's say $100 coming back in 1 year at 10% per year. So, what is the future value of an investment if I have $100 now? What would I have in 1 year? Well, to do this, we can use the equation from the previous slide, or we can also try to break it down from a common sense perspective. Let's try the common sense perspective right off the bat. The interest would be 10% of $100, so that's $10, right? So your value in your 1 year is going to be your principal, that $100, plus your interest, which is $10, so that's the $110. So your future value is $110. Now, if you look at the very bottom of this slide, you can see that we actually did the formula, just we didn't actually know we were doing it at the time, right? Because the future value equals 100 for the present value, and then in parentheses you have 1 plus 0.10. That 1 stands for 100%, and that plus 0.10 is 10%. So $100 times 110% equals $110. So the common sense approach or the formula approach, you're getting to that future value the exact same way. Now ask yourself real quickly, what if we held that money or that original investment for 2 years? How much money would we have there? We had started with 100, we went to 110. What would we have at the end of year 2? Okay, Ross, I'd like to switch now to the next slide. Now, many of you would have guessed $120. And that's a pretty logical guess. You got $10 after the first year, why not get another $10? However, it's important to realize that you also have compounding interest, meaning you have interest on interest. So you get 10% not only on the $100, but you also get 10% on the $10 that you got from the first year. So that's why you get $11 in the second year, and so $100 initially plus $10 of interest in the first year plus $11 of interest in the second year gives you $121. You could also just plug that straight into the formula here, as you will see, and you can write this as $100 for present value times 1.10 raised to 2, because in this case t equals 2. So and some people might also write that out where you have $100 times 1.1 times 1.1. I think using exponents makes a lot more sense, especially as these numbers get bigger. If that's exponent was 7 or 10 or 15, you wouldn't want to have to write 1.1 out 7 times or 10 times or 15 times. You'd want to be able to just succinctly write it using an exponent. Okay, Ross, I'd like to switch to the effects of compounding. So this brings up a good point. There's a difference between simple interest and compound interest. Simple interest is just the interest you would have earned on the original principal. So if you just looked at simple interest, then you would have had $120. However, when you include compounding interest, you get the $121. Because compounding interest not only includes interest that you earned on the principal, but also interest on interest. Okay, Ross, I'd like to switch to the effects of compounding. So if you're still confused, let's look at it one more time. Consider the previous example. The future value with simple interest is just 100 plus 10 plus 10, which equals $120. However, with compounding interest, you would get 100 times 1.1 raised to the number 2, which equals $121. So that extra $1 comes from the interest of the $10 of interest you made during the first period. Now, one of the things I like to do here is ask you, well, then what would you make after 3 years or 4 years or 5 years? Well, be careful to remember that you not only make simple interest and compounding interest from that first period, but then you're going to get interest on interest, right? And that's going to keep compounding over and over again. So let's take a look at that. Okay, Ross, I'd like to move on to the TVM example slide. So as you can see here in this graph or this table, we have a beginning amount, an interest earned, and an ending amount for different periods. So you're going to look just at the ending amount and you will see that you go from $100 to $110 to $121 to $133.10 to $146.41 to $161.05. So each year you make more money than you did the year before because of compounding interest. And the total amount of interest earned is $61.05, which is a lot more than what you would have made if you just had simple interest. In fact, what would it have been if you just had simple interest? The answer there would have been $50, right? So that extra $11.05 is compounding interest. Let's take a look at that. Okay, Ross, I'd like to go to the graph that shows the time value money. Looking at this graph, you will see that the gold represents your simple interest, whereas the blue represents the compounding interest. So the gold goes up by the exact same amount each year. However, the portion of compounding interest increases each year and will continue to do so, and you will have exponential growth because of the blue, whereas you would have a simple linear growth because of the gold. This is a simple illustration for the time value of money. And although this might not look powerful, there are lots of examples out there that can really show you how powerful this is. In point, I can lead to an example with the Indians. The Indians basically sold Manhattan Island for $24 worth of trinkets. Now, you might say Manhattan Island is one of the most expensive islands or pieces of real estate in the world. They obviously got a bad deal. Well, this was a long time ago, and had they actually had $24 to invest in the stock market and gotten anywhere, close to the average stock returns, let's just say 10% per year, that money would have over time become worth more money than there is in the entire world. So they could have pretty much owned every piece of the world, including Manhattan Island. So the time value of money, actually is far more powerful than most people think. Now, most of us aren't going to live hundreds and hundreds and hundreds of years unless, medicine gets better, but we do have a long enough period in our life to really take advantage of the time value of money, especially if you start to save when you're young. And that's, one of the reasons why I like to preach this so much to my class. If you'll take advantage of this now, this can really have a dramatic impact on your life down the road. Okay, I would like to show the Excel spreadsheet functions. Now you can also do all of this in Excel. And I've listed here the different Excel time value money functions. And I'm not going to go too much more into this, but I just wanted to expose you to them if you wanted to try to do some of the math in Excel as well. I'd like to switch now to future value important relationship 1. Okay, now that I've showed you how, the buttons on the calculator, the formula, and the Excel spreadsheet functions, I would like to talk about a couple important relationships for future value before we get into the math. The first one is that for a given interest rate, the longer the time period, the higher the future value. In other words, if you hold the interest rate constant, your money is going to increase in value over time. Okay, Ross, I'd like to go to future value important relationship 2 slide. The second important relationship for future values is that for a given time period, the higher the interest rate, the larger the future value. So in this case, the higher, the return, the more money you're going to make. This makes a lot of sense. If you're going to give me a stock that's going to give me a 10% return a year, that's going to be much better than a stock that gives me 2%. And that would actually be less than a stock that gives me 20%, right? So the higher the interest rate, the higher your future value will be. So both the R and the T can have dramatic positive and direct effects on the future value of an investment. Let me show you what this looks like in a graph. Okay, I would now like to go to the graph slide. The graph here of the time value money shows you the relationship with both the rate, which is increasing if you look at the graph at the far right from 0 up to 20%, and it also puts the time on the x-axis. So this allows you to see that both time and the rate of return will have a significant impact on the future value of an investment. Here we're looking at just $1, and you can see that if that interest rate is 0%, then over time nothing's going to change. But if it's anything above 0%, it's going to steadily go up. And if that number gets high enough, you're going to start to see that investment curve upward very steeply, and because it's an exponential function, right? So 20% is going to start growing very, very fast. And you would expect this and even demand it as an investor, right? Over time, you expect to make more money because you're taking risk. Once again, if you remember the example from the beginning of the lecture, if you're going to wait to get your $1 million check, you're taking a big risk there, and you expect there to be some kind of a reward for taking that risk. Also, you expect this investment to go up with a higher interest rate simply because of compounding. If it's 20% interest rate and you're getting not just simple interest, but interest on interest, and then interest on interest on interest, and so on and so forth, the higher that interest rate, the faster that compounding is going to allow that investment to take off. I think this graph also can tell you why it might be hard to decide when somebody should retire. Because what do you want your nest egg to be? Well, all of you will need at least a $1 million nest egg. That's right, you heard me. Not only Will you need $1 million to expect everybody in this class to be a millionaire before you retire? That might sound shocking, but that is something you need to go ahead and get in your mind. But how do you know when you're going to get the $1 million? Well, you can guess, but there are a few things you have to figure out. You have to figure out how long are you willing to wait till you retire, and then also what type of interest rate do you expect to get. And some of that will depend on the type of risk you take. And so if you take more risk, over time, your portfolio should grow faster. However, there's risk involved, right? And you could have a 2007 through 2009 type recession right before you were going to put your money into something safer and lose a big chunk of it, right? So, not everything is perfect. You can plug in numbers here and you can predict an exact answer, but that exact answer depends on the numbers you plug in, right? So there's assumptions being made. And that's why, deciding when to retire is not always easy for certain people. Let's take a look. All right, Ross, sorry, I've started there. I want to switch to this future value slide. Let's take a look at one of the problems on your test guide. Let's look at number 8 specifically, which is, focusing on future value. So let's read it. You are scheduled to receive $10,500 in 4 years. When you receive it, you will invest it for 10 more years at 5.5% per year. How much will you have in 14 years? Okay, this is where you need to identify what you're going to put in for each button on your calculator. So if you look at the time value money row on your calculator, it starts with N. So how many years? Well, the first thing that you want to figure out is, am I going to use 4 years, 10 years, or 14 years? So let's go back and read it. It says that you're not going to get the money for 4 years, so you can't do anything for 4 years, and then you're going to invest it for 10 years. So make sure that you put in 10 for N. So I'm going to type in 10 in my calculator and then hit the N button on that third row on your calculator. Okay, so it should say N equals 10. You don't have to hit enter or anything else after that. Now, what should I put in for my I button? Well, it tells me right away that it's 5.5% per year. So I'm going to put 5.5, and then I'm going to hit my I divided by Y button, and it should say I divided by Y equals 5.5. And then for my present value, it says you're going to receive $10,500. And in my mind, yes, you get that, but you didn't do anything with it for 4 years. Then you hand it over to somebody to invest. So that handing it over, in my mind, makes it negative. So you got to make either future value or present value negative. In my mind, I'm going to do present value in this case. So I'm going to do 10,500, and then I'm going to hit there's a plus minus sign at the bottom of your calculator. I'm going to hit that once, make that negative 10,500, and then I'm going to hit the present value button. And so it should say PV equals negative $10,500. Now I'm going to hit 0 and then the payment button because we're not dealing with payment. And that only leaves me with the future value button. Now, since I'm solving for future value, I'm going to hit the compute button, which is the top left button. It says CPT. I'm going to hit compute, and then I'm going to come over and hit the last button on the third row, which is the future value button. And it should automatically calculate that number as $17,935.52. Now remember, one of the most common mistakes to make here is that some students will add the 4 years and put 14 in for N, where it's only been invested for 10 years. So if you invest $10,500 for 10 years at an interest rate of 5.5%, you're going to end up making a future value of $17,935.52. So a couple more years and you probably would have doubled your money. Okay, I'd like to switch then to the next future value slide, problem number 9. Keeping with future value, let's take a look at question number 9. You have just made your first $5,000 contribution to your individual retirement account, assuming you earn a 10% rate of return and make no additional contributions, right? So you're only going to put money in one time for your entire IRA or 401k plan, I guess, which is not very realistic, but we're keeping it simple. What will your account be worth when you retire in 35 years? Okay, so if I wait 35 years and make N equal to 35, I equal to 10 for 10%. My present value is negative 5,000 because I put in $5,000. Payment is zero. My future value is going to be $140,512.18. That's right. So, if you put in $5,000 now and retire in 35 years, you've got $140,000 and already going towards that $1 million nest egg. Now think, if you do the $5,000 every year, how quickly you can get up and over $1 million. Once again, every one of you can and needs to become a millionaire before you retire. What happens though if you just say, I'm going to, goof off for 10 years and have fun? I worked hard in school, I deserve it, right? Well, if you don't save that money and you wait to 10 years and then make the $5,000 contribution, you only have $54,000 already going in that nest egg, and that's a huge difference, especially if you made this $5,000 contribution every year for those 10 years before then, because we're not just going to add these amounts together. Remember, these amounts are going to also be getting compounding interest on top of the simple interest. So you can make quite a lot of money. In fact, you could have already pretty much had your nest egg built up to the $1 million before you even got to 10 years down the road if you did the $5,000 every year before the first 10 years. So those investments you make early on are very, very, very important because they get to take advantage of the time value money for the longest amount of time. That is just such a crucial point for this class. Start saving now. It'll just mathematically do you, in your nest egg a huge, huge, huge favor. Okay, Ross, I'd now like to switch to number 10 slide. In fact, let's look at problem number 10 to show the difference between simple interest and compounding interest. Second Union Bank pays 6% simple interest on its savings account balances, whereas Third Street Bank pays 6% compounded annually. Now, if you made a $10,000 deposit today in each of those two banks, how much more money would you earn from your Third Street Bank account at the end of 15 years? Now, why does it just assume that? Well, Third Street Bank is doing compounding, so you would expect there to be more money there. Now, to do this, let's first compound the simple interest. That's real easy to do. I gave you an equation. In fact, that seventh equation written at the top of your test guide we're going to finally use that, where your future value equals the present value plus the simple interest times the number of years. So for Second Union, you're going to have $10,000, which is going to be your present value, and then you're going to have $10,000 times 6% to get the simple interest per year. So that would be $600, and then you're going to multiply that times the number of years, which is 15. So $600 times 15, that equals $9,000, and if you add that to the $10,000, you get the $19,000. Okay. Now Third Street is just using your time value money buttons, right? You're going to invest for 15 years at an interest rate equal to 6, a present value equal to negative $10,000. Payment is zero, so I didn't even show that, and then the future value is $23,965.58. Now, if you subtract those two numbers, the difference is basically compound interest, right? So compounding interest gives you almost an extra $5,000. It's pretty powerful, and that was only for 15 years. It had been a much, much bigger deal, over 25 years or 35 years because of the exponential function of compounding. I'd now like to go to slide number 13. Now let's look at one more future value problem, number 13. Today, Tony is investing $26,000 at 5.5%, compounding annually for 5 years. How much additional income could he earn if he had invested this amount at 11%? Okay, so now we get to look at what happens if you take more risk and invest at a higher interest rate. So using your time value money buttons, you're going to put n equals 5 both times, and the I is where the difference is. And the first time you're going to try 5.5%, like pretend that might be like a bond fund or something like that. And then the second time you'll use 11%, which is maybe more like a stock fund. The present value is going to be negative $26,000, payment zero, and you calculate the future value. And you'll see that you just by taking on that more risk that you would have close to $10,000 more from investing in stocks than you would in bonds. This proves one of the biggest rules in finance, which is that there's a direct relationship between risk and return. The more risk you take, the higher your return. So now that we have gone over a couple different ways to look at future value, let's look at the other three, the number of periods, the interest rate, and present value, with maybe less examples, but we'll cover them in a similar fashion. Let's start with present value. Okay, Ross, I'd now like to go to the present value slide. Okay, so present values are the current value of future cash flows discounted at the appropriate discount rate. That sounds like a mouthful, but basically it's saying what would you pay today for what you're promised to get down the road. Okay, they're always going to have a value of 0 on the timeline. And once again, it answers the questions: how much do I have to invest today to have the same amount in the future, or what is the current value of an amount to be received in the future? Okay, Ross, I'd like to move to the next slide. Now, why would present value be worth less than the face value? Well, there's two major reasons. One is opportunity cost, which basically means that when deciding between investment options or opportunities, you always have to consider what you could have used that money for as well, or your time. So one opportunity cost that I think speaks quickly to students is video games. I recently read that video games cost students somewhere around $200 a year. Now, whether or not that's true, that amount, in the article was made to be some huge amount. To me, that's nothing compared to the opportunity cost of playing the video games, meaning what else could you have been doing with your time? I mean, unless you're going to become a video game designer, it's not a really good use of your time to learn how to, solve all these epic quests that, take 200 to 400 or 500 hours to beat. When you could have been spending that money getting a good grade in Finance 3020, getting to know your professor in Finance 3020, finding out about internship opportunities, getting a good job, making lots of money down the road. There's a lot of time management issues, or opportunity costs associated with playing video games. And other people have other vices as well. I'm just using video games as one. So make sure that you understand that there are opportunity costs in most decisions that you make. There's also risk and uncertainty. You don't know what's going to happen, and the riskier something is, the more the more of a return you expect down the road. If you tell me I'm going to invest in very small companies and buy stock in very small companies, that's very risky and I expect a very high return. Whereas if you tell me that I'm going to buy a treasury bond from the U.S. federal government, then that's not very risky at all, and so I would not expect to get nearly the same amount of return. Okay, Ross, I'd now like to go to the present value slide that has the equations on it. So most of you will solve these problems using time value money buttons on your calculator. However, you can also use Excel or the equations, right? And so if you want to rearrange the original equation for a present value, you can basically see that all you're going to do is divide both sides by 1 plus r raised to the t power. This is often called discounting, and in this case the r would probably be at more a discount rate, because you're finding the present value of one or more future amounts. All right, now I'd like to go to the important relationship slide. Now, just like the future value, there are some important relationships with the present value. So for a given interest rate, the longer the time period, the lower the present value. So this is pretty much opposite that you find with future value, because the more time that goes by, the longer you have to discount those cash flows back to the present value, so the present value is going to go down. For example, if you told me that you had an investment for me, but you could give me my money back in 5 years, well, that's one thing. But if you said you couldn't give it back for 25 years, that's something totally different. And so the present value of that investment has gone down to me because I've had to wait so much, further, into the future to receive the money. So if I'm going to figure out its present value, I'm going to have to discount it back over so many periods. So as t increases, the future value may go up, but the present value would go down. So let's move on to the next slide that shows the timeline. So let's take a look at that specifically on a timeline to prove that point. What is the present value of $500 to be received in 5 years, 10 years, using a discount rate equal to 10%? Okay, so if you're going to pay me the $500 back over 5 years with an interest rate of 10%, its present value is going to be $310.46. If it's going to be the exact same thing over 10 years, then now we are looking at a present value of $192.77. So obviously I don't want to wait an extra 5 years, so its value to me is less. So notice that there is, there was no real money up front, so we're just getting this, $500 in 5 years or $500 in 10 years. Well, obviously I'm going to take it in 5 years, just like anyone in my class would do the same thing as well. Ross, let's move on to important relationship 2. Now the second important relationship is that for a given time period, the higher the interest rate, the smaller the present value. So this is also opposite, for present value than it was with future value. In other words, as the interest rate increases, the present value is going to decrease. This makes a lot of sense because you're going to be discounting back at a higher rate. So the higher that discount rate, the faster the money discounts back to a smaller number over time. So if you discount a future value at 15%, it's going to be much smaller by the time you get back to t equals 0 or the present value than if you only discount it by like 1%. To prove my point, I'll show you this in a graph. Okay, Ross, let's take a look at the graph. So in this graph, the time value money, this looks, almost opposite of the graph I showed you before, which is that if I take different amounts of money on the y-axis and I discount them back over time, they're going to be worth more today, right? And that number would have to be much lower if I'm using a higher discount rate, right? So, for example, let's say that you could have $1 today. That's only worth $1 in the future if r equals 0%. However, if you're going to be using higher discount rates, those are going to have a larger and larger impact on the present value of that investment. So the higher the r value, or the discount rate, the lower the present value for that project. This would be a good time to introduce the concept of required return, because if you think of discount rate as what the company requires, you will see that the more that you require from an investment, the lower its present value will be to you. So if you keep your money in a checking account that doesn't give you any interest rate, well, you don't really expect a change between the present value and the future value of your money, right? So $10 in the future should be worth $10 now. Whereas if you are going to be putting it in a very risky stock market fund, then where you expect to get 10%, 15%, or maybe even 20%, that number needs to be much higher down the road because you require that much higher return because of the risk involved. Now that we've talked about the definitions and the equations and seen it in a graph, let's try a problem that maybe hit home the basic idea of present value. All right, Nick, let's go to the present value problem, number 12. So this is a very common problem that I think will make a lot of sense to you very soon after you graduate, especially if you expect to become a homeowner. Number 12, you want to have $30,000 for a down payment on a house 10 years from now. Now, if you can earn 5.5% compounded annually on your savings, how much do you need to deposit today to reach your goal? Okay, now think about that. To get the loan, we need to have $30,000 down payment. Now, why 30,000? Well, anybody knows anything about a loan on a house, usually you put down, at least 20% to avoid PMI or private mortgage insurance. So in this case, this could be somebody that's wanting to buy a $150,000 house, right? Now, to get the $30,000, they need to know how much they need to invest today, right? So the future value is going to be $30,000. The payment is going to be zero. We're not really dealing with that. They know they're going to want to get that house 10 years from now, so the end's going to be 10, and they expect to make 5.5%. So you plug those into your calculator, you hit compute PV, and you're going to get a present value of $17,562.92. So, as we were talking about with the slide before, one way that you can make that present value go down is by maybe investing that money in something riskier, higher than 5.5%, or by investing that money longer. So you'd have to, to get the PV to go down, you'd have to either increase N or increase I, and that would mean that you would need, to start off this investment project with less money than $17,562.92. All right, let's go to the basic PV equation refresher slide. Now we've covered, future value and present value, but remember there are four parts to this equation. There's also R and T, or the interest rate and the number of periods. If you know, any three, you can obviously solve for the fourth using the equation. And there's also a reminder here to remember about, sign convention, which is not too complicated at the moment as long as you keep, one of them negative. Okay, Ross, let's go to the interest rate slide. So after future value and present value, let's talk about the interest rate. Now, to find the interest rate, we can rearrange like you see, in this slide, and then you're getting something slightly more complicated. It's obviously a lot easier to use the buttons on the calculator, but this is completely doable, especially if you understand how to use the exponent buttons on your calculator, like the y raised to the x. That would be, that's usually the button that I use. Okay, let's go to the number 15 slide, Ross. Now, although you can use the equation, most of you will use the buttons, which makes it a lot easier. And I'll show you this with a problem here from your test guide. Look at number 15. You have $10,100 today, and you'd like to quadruple your money, not double it, not triple it, but quadruple it in 10 years. What interest rate must you earn if the interest is compounded annually? Now, you know that it's 10 years, so N would be 10. You're solving for I. Your present value is negative $10,100. Your payment is zero. So what would future value have to be? Well, just quadruple it, right? So that would obviously be $40,400. You solve for I, and you get 14.87%. Now, you could have also, quadrupled any amount, and you'd gotten the right I, right? So you could have, used $1 or -1 for present value, and then just used 4 for the future value. So that's somewhat of a shortcut, meaning, I could ask this problem on an exam and not even mention the $10,100 today. I could just say, how long is it, or what interest rate do you need to quadruple your money in 10 years? That's it, right? And you should be able to solve that problem. Let's look at the other interest rate slide, number 16. Now there's another way to look at the interest rates. Let's look at number 16. Assume the total cost of a college education will be $385,000 when your child enters college in 18 years, which is probably going to be a lot higher than that, but especially the way education expenses have been inflating over time. Nonetheless, let's go with it. You presently have $65,000 to invest. That's a lot of money, by the way. So what annual rate of interest must you earn on your investment to cover the cost of your child's college education? Okay, so you're going to invest for 18 years, N equals 18. You're going to solve for I, so skip over that. Present value is going to be $65,000, negative $65,000, because you're investing money into the system. Payment zero. Your future value, which is the amount you need to cover your child's expenses, is $385,000. So you solve for I, or hit compute I, and you get 10.4%, right? So, even with a huge investment right now, if you just had a child today and you invested it, you would see that it would take you a pretty risky investment to reach your goals, right? You're going to have to be in something that's, predominantly an equity fund or something with similar risk. Now that covers two different interest rate problems. The last problems we will look at will cover the fourth variable in the general, time value of money formula, and that is the number of periods. Okay, Ross, I'd like to go to the finding the number of periods slide. Now, let me start by showing you how you would rearrange the equation for finding, t, or the number of periods, using the general formula. Because you're solving for the exponent, you're going to end up using natural logs, which, scares a lot of students. It's really not as complicated as it looks, but it's certainly slower than using the time value money buttons on your calculator. So that being said, I'm just going to show you how to do it with your calculator. Okay, Ross, let's go to the example. Let's look at a quick example. You want to purchase a new car and you are willing to pay $20,000. If you can invest at 10% per year and you currently have $15,000, how long will it be before you have enough money to pay cash for the car? Okay, now you can put everything in the buttons and solve for n, and you get 3.02 years. You could also do it in Excel and get 3.02 years, which just reminds me that, obviously, why would you do it in Excel if you can do it so much faster? Well, a lot of people like to use Excel to check, or in the real world, you might have to keep all of this information stored somehow, or, some kind of a record of it. And so Excel is obviously very good for that as well, especially if you're going to be doing very complicated calculations with a whole lot of numbers. Then you can obviously do a lot of that in Excel very fast. All right, I'd like to switch to the next slide that shows the equation. So you can do it with your buttons, or you can do it with your, in Excel, or you can use the formula. So if we look here at the formula, you're going to see it's pretty interesting. Now, how do you do it? Well, let's walk through the algebra real quick, since some of you may be a little bit confused. The first thing that you would do is that you're going to figure out what, the future value over the present value is. So 20,000 over 15,000 is 1.333 repeating. Now, if you use the LN button on your calculator, and some of you are like, LN button, it is on the first column of buttons. It's the fourth row from the bottom. To use this button, in this case, all you would do is hit 1.333, and then you would hit the LN button, and it should automatically change your number to 0.287, in my case 43. You'd also use the LN button for the number in the denominator. In this case, that's 1.10. And once you have those two numbers, then you just, take the ratio or divide the numerator by the denominator, and you're going to get that 3.02. So it really doesn't matter which way you do it. You can do it using the equation, using the time value money buttons, or the Excel spreadsheet, or you can do all three to check, but they should all give you the exact same answer. Now let's look at a couple problems on your test guide to wrap up this lecture. Okay, Ross, I'd now like to switch slides. Problem number 7. Looking at problem number 7, we have a very good number of periods problem. You expect to receive $22,000 at graduation 2 years from now. Now you plan on investing it at a 9%, rate of return until you have $150,000. How long will you have to wait from now? All right, so let's figure that out. You're going to skip over the N button. You're going to make your I equal to 9 for the 9%. Present value is going to be negative $22,000 for the $22,000 investment that you will put into the system. Payment is 0, and you want $150,000 down the road, so that's your future value. Hit compute in, and you get 22.27 years. So you're going to have to wait a little over 22 years to reach that $150,000 mark. Now, is that the correct answer? Look at step 3. The correct answer will actually be 24.27. Make sure you remember that you had to wait 2 years before you even got the money. So that's a little bit of a trick in there, but it's just to make sure that you realize that it's not all about just putting the numbers in the buttons and hitting compute, that you have to conceptually understand what's going on in the problem as well. Okay, Ross, I'd like to go to number 11 slide. Now let's look at number 11. How long will it take to double your savings if you earn 4.6% interest compounded annually? Now remember, previously I told you that if you have to double your money or triple or quadruple, you can always use $1 as your present value, and that would be obviously a negative one. And then whatever that amount is, you can make for your future value. So if you need a double, future value will be 2, triple, future value is 3, quadruple, future value is 4, and on and on. So in this case, future value would be 2, and payment is 0. So just by saying double your money, that takes care of PV, payment, and FV buttons, right? So what's left is the I button, where we're going to earn 4.6%. So put that in, you solve for N, you realize it's going to take you 15.41 years to double your money. Now, another thing that's interesting about doubling your money is that there's a rule called the Rule of 72. And I'm just going to talk about it briefly, but basically what the Rule of 72 says is that you can take the number 72 and divide it by either your number of periods and get your interest rate, or you can divide it by your interest rate and get your number of periods. And that Rule of 72 tells you, how long it'll take you to double your money, or what interest rate you would need to double your money over that amount of time. So in this case, we would have done 72 divided by 4.6, and I would have gotten 15.65 years. So that is just like a rule of thumb. It's not going to give you the perfect answer, but it's a good quick way to check and make sure you're in the right ballpark. That number is only exactly right, if you're around 8 years and a 9% interest rate, or 9 years and 8% interest rate. And then as you get further away from those numbers, you're going to end up getting a little bit further away from the exact right answer. Nonetheless, it's called the Rule of 72, and that was very popular, especially before you had all the time value money buttons. Not used as much today, but it's not a bad real quick check method. Okay, Ross, I'd like to look at number 14 slide. Now for our last problem, we're going to look at number 14. You want to invest an amount of money today and receive back 3 times that amount in the future. You expect to earn 6% interest. Approximately how long must you wait for your investment to triple in value? Now, once again, we're going to just make present value -1 in this case. Future value would be 3 for tripling. Payment is 0, so that takes care of those. I equals 6, and you solve for N, which is 18.85. So it's going to take you 18.85 years here for that investment to triple in value. Now, what's interesting is that, I just told you about the Rule of 72 for doubling your money. There's also the Rule of 114 for tripling your money. So in this case, we would take 114 and divide it by 6, and you'd get exactly 19 years, right? So that's very close to 18.85 years. So once again, it's an approximation, but it works pretty well. There's also, by the way, a rule of 144 for quadrupling your money. So there are some very quick rules here for checking if you want to add those to your toolbox. Okay, Ross, I'd like to switch to the last slide, which is a summary of formulas. Well, that's pretty much all the problems and all the material. This last slide is simply a summary of the formulas that you can use almost like a cheat sheet if you wanted to have all of that information in one specific slide or one place to go to for studying. This concludes lecture 2.2, Time Value of Money. If you have any questions, please let me know. Thank you.